family of functions is a group of functions with graphs that display one or more similar characteristics. A parent function is the simplest of the functions in a family. This is the function that is transformed to create other members in a family of functions. In this lesson, we will study 8 of the most commonly used parent functions, and you've seen this before. Now, looking at linear and polynomial parent functions, we begin with the general equation of a constant function, which is f of x equals c, where c is any number. Now, this is what it would look like, a horizontal line. So we would have y equals 2, or we could have y equals 0.5, which would be a horizontal line. Now, when c equals 0, f of x is the 0 function, which is essentially along the x-axis. So this is y equals 0. The identity function f of x equals x passes through all points with coordinates a. So essentially, the x and the y values are equal. So this is what the graph would look like. So if you pick a point here, you can see this has coordinates 2, 2, 1, 1, 0, 0, minus 1, minus 1, minus 2, minus 2. The parent function of quadratic functions is f of x equals x to the power of 2, or x squared. And this is what the graph would look like. So you can see it's a U-shaped graph, otherwise known as a parabola. Finally, the parent functions of cubic functions is f of x equals x to the power of 3, or x cubed. And this is what the graph would look like. The square root function has the form f of x equals the square root of x, and this is what its graph would look like. The reciprocal function has the form f of x equals 1 over x, and its graph would look like the following. The absolute value function, denoted like so, is a v-shaped function defined as f of x equals negative x if x is less than 0, f of x equals x if x is greater than or equal to 0. So if we had the absolute value of negative 5, okay, so it's in this scenario, because it's a negative number, we simply assign a negative sign at the front of it. So if we attach a negative sign there, these two negatives turns this into a positive 5. So essentially a negative number, if you take its absolute value, it will become positive. So the absolute value of negative 2.5 is 2.5. 0 and 3 are both greater than or equal to 0. So it will stay the same. So the absolute value of 0 is 0. The absolute value of 3 is 3. And this is what the graph of the absolute value function looks like. Now we can see, if we look at the negative side of the x-axis, we can see this is negative 1. It became positive 1. This is negative 2. It became positive 2. This is negative 3. And the y value became positive 3. Now, because the absolute value function is defined in this way, this is also why it's known as a piecewise defined function. The greatest integer function, denoted like so, is defined as the greatest integer less than or equal to x. So, for example, let's look at the greatest integer which is less than or equal to negative 1.5. Well, let's look at a number line. You can see negative 1.5 lies between these two integers. So we want the greatest integer which is less than negative 1.5. So it has to be negative 2. So what's the greatest integer which is less than 1 over 3? Well, we can see it lies between 0 and 1. So 0 would be the greatest integer which is less than 1 over 3. So we write down 0. And we can see negative 4 is already an integer. Okay, so this part here, or equal to x, this is where this would come in. So the greatest integer which is less than or equal to negative 4 is negative 4. And the graph of the greatest integer function would look like this. Now, this is also a piecewise defined function. Now, you can see from the graph that it looks like a set of stairs, which is why we also call it a step function. Now, there are other step functions, but the most well-known step function is the greatest integer function. Example 1. Describe the following characteristics of the graph of the parent function f of x equals the square root of x. So we want to describe the domain, range, intercepts, symmetry, continuity, end behavior, and intervals on which the graph is increasing or decreasing. So the first thing I would advise is to sketch or draw the graph of the square root function, which looks like this. So let's begin with the domain. The domain is the x values. So we can see it starts off at x equals 0 and it continues to increase in the positive x direction, unbounded towards positive infinity. So we write this interval down for the domain. Now for the range, we look at the y values. So it begins at y equals 0 and the y values continue to increase unbounded towards positive infinity. So we write this interval down for the range. Now you can see there's only one point of intercept, which is over here, and it has coordinates 0, 0. This is definitely not a symmetrical graph, which means the function f of x is neither odd nor even. And there's no points of discontinuity. So this graph is continuous for all values in its domain. And when we want to look at the end behavior, well, the graph begins at x equals 0. Okay, what happens to the function as x goes towards infinity? Well, this function is increasing unbounded towards positive infinity. So this is how we would write it down. The graph begins at x equals 0 and the limit of f of x as x tends towards infinity is infinity. And we can clearly see here the graph begins at x equals 0 and it continues to increase. So this is an increasing function, okay? And the graph is increasing on this open interval here, 0 to positive infinity. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Now transformations of a parent function can affect the appearance of the parent graph. Rigid transformations change only the position of the graph, leaving the size and shape unchanged. Non-rigid transformations distort the shape of the graph. Translations are an example of rigid transformations that has the effect of shifting the graph of a function, and we have two types, vertical and horizontal translations. Now looking at vertical translations, we have this function g of x being equal to f of x plus k. So we have this function f of x being transformed, okay? We add the value k. Now because this k plus k is on the outside of this bracket, it affects the y values. So when k is positive, the graph of f of x moves k units up. And when k is negative, the graph of f of x moves k units down. Now looking at horizontal translations, we have the graph of g of x when it's equal to f of x minus h. So be careful, we have x minus h, so it's a negative h here, whereas over here we have plus k. Just be careful of this here. Now because this is within the bracket, this affects the x values. So when h is positive, the graph of f of x moves h units to the right. And then when h is negative, the graph of f of x moves h units to the left. Example 2a. Use the graph of f of x equals the absolute value of x to graph each function. So the graph of the absolute value function would look like this. This is the parent function. Part A. G of x equals the absolute value of x plus 4. Now this absolute value of x can be replaced with f of x. So we can write it like so. Now because this plus 4 lies on the outside of the bracket over here, this tells us it'll affect the y values. So because this is positive, that'll tell us the graph of f of x would be translated 4 units up, like so. Part B, g of x is equal to the absolute value of x plus 3. Now, because this plus 3 is within this absolute value sign, we can replace the x over here with an x plus 3. So we can replace the x here with an x plus 3. And we can rewrite this, okay, as g of x is equal to the function f of x plus 3. Now, because this plus 3 is within the bracket, this affects the x values. Now, we have to be careful. If you recall, we defined the transformation as x minus h within this bracket. So we have a negative h. This tells us negative h is equal to positive 3. So h is equal to negative 3. So h is a negative number. So that tells us that the graph of f of x will be translated 3 units to the left, like so. Part C, g of x is equal to the absolute value of x minus 2, subtract 1. Now what we'll do is, the x over here we'll replace with x minus 2, so we have something like this, and then we'll write the minus 1 on the outside like so. So this tells us the graph of f of x will be translated 2 units to the right and 1 unit down like so. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. So reflections is another type of rigid transformation, so it doesn't change the shape or the size of the graph. So for a reflection in the x-axis, we have g of x is equal to negative f of x. So the negative sign there is outside of this function, okay? It's at the front of this. So the parent function f of x is then reflected in the x-axis to give us this mirror image in green. Now with reflections in the y-axis, we have g of x is equal to f of negative x. You can see where the negative is, it's within the bracket over there. So if we have the original parent function here in blue, this would be reflected in the y-axis to give this mirror image in red. Example 3a. Describe how the graphs of f of x equals x squared and g of x are related. Then write an equation for g of x. So the first thing to do is to draw the graph of f of x equals x squared, like so. And you can notice straight away that this graph in red has been reflected in the x-axis. Okay, and it's also been translated 1 to 2.5 units to the right. Now, because the reflection took place in the x-axis, we need to write down a negative sign in front of the function f. And because what we have here is a horizontal translation, within the brackets we write down x minus 2.5. So we can rewrite this now as the following, which is the equation for g of x. Part B, again we'll start by drawing the function f of x like so, and we can see straight away that this graph in red, f of x, has been reflected in the x-axis. Okay, and we can see a translation has taken place and it's been translated 1, 2 units up. Now because it's been reflected in the x-axis, we need to write down a negative in front of the function f. And this is a vertical translation, so we write down +2 outside of this bracket. And then we can rewrite this as the following, which is the equation for g of x. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Dilations are a type of non-rigid transformation, so it will affect the size and the shape of the graph. Now if you look at the vertical dilations first, g of x is equal to a multiplied by f of x. If a happens to be greater than 1, then the graph of f of x will be expanded vertically. Now, if a happens to be between 0 and 1, then the graph of f of x will be compressed vertically. Now, for horizontal dilations, g of x equals f of a multiplied by x. So a is now within the bracket multiplying x. If a is greater than 1, then the graph of f of x is compressed horizontally. And if a is between 0 and 1, the graph of f of x is expanded horizontally. Example 4. Identify the parent function f of x of g of x and describe how the graphs of g of x and f of x are related. Then graph f of x and g of x on the same axes. Part A. G of x is equal to 1/4 multiplied by x cubed. So to identify the parent function, because this is x cubed, we know f of x is equal to x cubed. So let's draw this in first. Now we can see x cubed can be replaced with f of x, so we can rewrite g of x as 1/4 multiplied by f of x. Now, because 1/4 lies between 0 and 1, we know that the graph will be compressed vertically like so. Part B, g of x is equal to negative, and then within brackets we have 0.2x all to the power of 2. Now because we have an x squared term, we know that the parent function f of x is equal to x squared. So we draw this in first. Now outside the bracket we have negative sign, and then within the brackets we have 0.2x. So we'll write g of x like so. So you can see this negative sign goes on the outside of the function, and the 0.2x has replaced the x to give us this. Now the graph of g of x, okay, transforms the graph of f of x with 2 transformations. Okay, so we'll start with within the bracket first. So because 0.2 lies between 0 and 1, we know that the graph will be expanded horizontally to give us the following. Okay, and then finally, because of this negative sign on the outside, we know that the graph of f of x will also be reflected in the x-axis to finally give us g of x. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Now just to summarise, here are the 8 basic parent functions, and you should be able to recognise, recall and graph them quite quickly, as they will help you when you are asked to graph their transformations. So just summarising the translations, remember we have 2 types, a vertical translation and a horizontal translation. Now look at the vertical translations. Okay, we have g of x is equal to f of x plus k, where f of x is the original parent function that we have in blue. Now if k is greater than 0, then the graph will move k units up. If k is less than 0, then the graph will move k units down. Now looking at the horizontal translation, if we have g of x is equal to f of brackets x minus h, where f of x is the original parent function in blue that we have over here, then if h is greater than 0, the graph will move h units to the right, and if h is less than 0, then the graph will move h units to the left. Now remember, translations is a rigid transformation, which means the size and the shape of the graph won't change. And just to recap reflections, if we have g of x is equal to negative f of x, so we have this negative sign in front of the function f of x, this essentially multiplies the function f of x with a negative number. So this means that the parent function in blue here, f of x, will be reflected in the x-axis. And if we have g of x is equal to f of negative x, so within the brackets here, we can see x is being multiplied by a negative number. This means that the parent function f of x in blue here will be reflected in the y-axis. And reflections is another example of a rigid transformation, so it doesn't affect the size or the shape of the function f of x. And finally, to review dilations, we have 2 types, vertical and horizontal dilations. Now, for vertical dilations, g of x is equal to a multiplied by f of x. So f of x is being multiplied by a number a. However, if a is more than 1, then this parent function f of x in blue will be expanded vertically. If a, however, is between 0 and 1, then this graph of f of x will be compressed vertically. Now for horizontal dilations, we have g of x as being equal to f of a multiplied by x. So within the brackets, x is being multiplied by the number a. However, if a is greater than 1, then the graph of f of x will be compressed horizontally. And if a is between 0 and 1, then the graph of f of x will be expanded horizontally. Now dilations is also a type of non-rigid transformation, which means it will affect the size and the shape of the graph of the parent function.